Hello, I'm Mark Kotanchek, the CTO of Involved Analytics. Today I will be talking about life doesn't have to be hard, wherein we use our data modeler software to easily handle multivariate data, extract insights, and to handle missing data and correlated data, all the things that are associated with the real world. Topic of the day, I should have titled it is Life Doesn't Have to Be Hard. The reality is data science doesn't have to be hard. So I probably should have made that a little more clear. Anyhow, one of the things that happened in my history is I started off working in industry and discovered that, as those in that world know, they're great at collecting data, they're great at doing records retention, but extracting the insight out of multivariate data efficiently is difficult, it's intrinsically hard. So what we'll see today is something that has had a close to 20-year gestation to get to this point. Basically, the idea is that let the data speak for itself, handle real-world data with correlated variables, lots of variables, missing records, missing data within records. I mean, you've just got to be able to roll through that. I mean, if you look at a lot of the analysis tools, you have to go through and form a perfectly numeric matrix. You've got to do a lot of pre-processing to get something that's suitable for the algorithms, which means every single path you chase down, you're building more and more different data sets. So with that introduction, I'll talk about the tool here is Data Modeler. Trying to get this screen matching properly. Yeah, all right, good enough. And so Data Modeler started off as a function package. So we have roughly 450 functions that are built in Data Modeler. These are accessible for the power users. They're exposed. They're excruciatingly well documented. But the problem is, I mean, you go out and, so okay, this is strictly for Mathematica community users. You have to be able to hit Shift Enter and know what you're doing. Recognizing that was an issue, started working at building a GUI. And what we have here is just basically you throw the data in. The assumption is, coupled, that you're within you can create a flat file database with a header row, data, Excel, CVS, whatever. Comes into Mathematica. And at that point, the computer, the algorithms have to support the user. You don't support the algorithm. And the presumption that we're going to do is that data lives, even though we have lots and lots of variables, that would actually where the things that we care about are a relatively small subset of variables. So we're going to try to identify the key variables, try to build models against them, extract insights about relationships, those aspects, and eventually start pulling out models that we might deploy. And furthermore, because of the path that we're following, we're able to build trustable models. So the first example here of preloaded, the presumption is that I'm going to pick a target variable. So this is a training problem. Predictive analytics would be another word for it. Pick a target, and I'm going to go figure out what's happening. Step one is to get the Zen of your data. The Zen is it's important because it sort of tells you what you want to do. In this case, this is a distillation column from a chemical plant. We have lots of correlated variables. Blue is highly positive correlated. Red, the darker the red, it's negatively correlated. I mean, and this is sort of a real-world situation. One of the neat tools, and again, all these things are available as exposed functions for the power user to build custom workflows, is to look at the data sets and say, is it, what's the distribution look like? Is it quantized? Do I have something that's on a log function where I want to maybe do some scaling on that? Is it possibly quantized? How complete is it? Plotting the data, these sorts of things. And I think this one's sort of interesting in that we detected that a couple of the variables were quantized and looked like they, so the display automatically shifts to be able to reveal that information and to more accurately display results. I mean, I think this is 8,000 data points, something roughly in that ballpark. In this case, this is a purely numeric matrix, so we have all good stuff. But I wanted to use this example because, there we go. I ran a bunch of modeling runs to get to the in here. What we're doing in the model search is we're looking at, we're generating random models, just nothing, using the variables at hand, building models, and then from those, rewarding those that are both simple and accurate. So we're rewarding two things, and we're doing an evolutionary process. And over time, unnecessary variables get pushed out, unnecessary complexity gets pushed out, model accuracy increases. But what we're doing is we have a population of models, and these are, they may be a little small, that's what you see is we're evolving algebraic expressions. So rather than assuming that the world's a second order polynomial with no cross terms, we're letting the data decide what's an appropriate model. Now, the thing is, because of the stochastic nature of this, we have lots of different paths to success. We have lots of different models which can come to the fore and be approximately equal. So if I move to the Analyze tab and shift to, in this case, a little twitchy. There we go. Don't double hit. So if we shift to this view, and this is a view of all of the models which were created in these 16 5-minute model searches or 3-minute model searches, what we see is sort of lots of different structures. Now, from the point of view of deploying something, they're all roughly equal. I mean, they're reasonably accurate, and in this case, extremely accurate, better than 98% R squared, and reasonably simple. So we're going to prefer, if we will, a model like this, which is fairly compact, has a handful of variables, as opposed to something I'm over the tooltip limit. This model out here is just, doesn't give us any more in terms of accuracy, but adds a lot of complexity, so we don't like that. So I'm going to move over. I've loaded in, I've done a couple modeling rounds, and so now I've loaded in the round 3 contenders, which I've archived off onto disk. And so what you do during the model searches is you're looking for, say, which variables are coming to the fore. So So my initial exploration got me lots and lots of decent models. I'm going to choose a subset. I'm going to choose a subset that are interesting. Okay, evidently loaded the wrong data set in, or didn't load it in. There we go. All right, so now I've got a bunch of models that I've loaded. Now these, so of 400 plus models, and I want to say what does this mean? Well, first I'm going to say, how many variables are required to get to something decent? So this particular chart this is the distribution of the number of variables in the developed models. But of the models with 3 variables, I have different paths of success. So reflux flow, temperature tray 1, vapor flow seem to have been pretty popular. I got pretty good models out of the deal. If I go to 4, I get more variables, but I've also got different paths, different combinations of variables. Now this is important to look at the possibilities of your variable selection, because I might have, in a real world problem, I would prefer controllable variables over things that are simply measurements. So if I'm doing social science type thing, if I've got a knob I can tweak to control things, I'd rather have that knob in my models rather than something like latitude. Where it's, yes, there's a correlation, but it's not a controllable correlation. I can go through and, based upon this insight, I can look at which variables have come to the fore. And now here I'm focused in on, a handful have really sort of popped up, and I could start focusing down. I'm going to slowly iterate down and see which ones really count. I can look at variable combinations. And what I've done here, just in the interest of time, I've picked out a few models. And so eventually I went through and I decided I wanted to really had 3 variables was going to be enough. These 3 variables, I do some more modeling. And these models are, so I've got close to 200 models. They're all different. They're all unique structures. Let's take a look at what, how they perform. So if I look at an individual model, this one, there's one, and I look at its prediction plot, which is error versus observed versus reality. I get a distribution sort of like this, where so we shifted because we had so many data points. We automatically shifted to a density plot to show where the thing was, because otherwise you just have this sort of all these blue dots lined up, and you don't have an idea that really you're fitting the majority of the data pretty well. If I shift to a different model, I get a slightly different result. So what do I do in this circumstance? How do I pick the model? And remember, we're dealing with real world data, so it's got noise in it. I'm not sure I measured every variable that actually mattered. Well, one solution is to use an ensemble. So an ensemble is fairly simple. It's just, I'm going to take all those models that I defined as sort of good enough in being both simple and accurate. and I'm going to choose a diverse set of those. And this supermodel has a special property. Now, so it's going to predict well where there's data, because otherwise it wouldn't be a good model. But because we've explicitly chosen them for their diversity, if we ask that model to go into a new region of parameter space, or the underlying system changes, then we're going to get a heads up that this thing should not be trusted. You know, I've got a prediction for you. Now, the problem with the model is it's a big pile of trust me. With these supermodels, you've got a prediction that generally behaves pretty well in extrapolation, but also you've got the warning that you should proceed cautiously. This particular data set okay. Oh, okay. Have the same display up. So here, okay. So I'm going to load in. I don't want to do that. I'm going to jump to load in a couple individual models rather than population. Yeah, so let's take a look at. What I want to do. Let's not do that one. I'm going to do my individual models, and I want to see how they perform against two data sets. So I've got a training data set and a test data set. Now, my contention personally is that I prefer to have my models be the most informed that I can make. I want them to be exposed to all of the data. I'm going to rely on this ensemble nature to give me the best data. If, however, I look at my my two models, and I'll do my ensemble as well. If I look at my prediction plot, this particular data set was chosen to test extrapolation. So you see that the one model fits sort of well, but then we're missing the middle data, and we've got the extremes that haven't been covered. Those are so that information's there, but if we go to a ensemble and we look at the prediction plot, we're going to look at a response plot. Double clicks. All right, so the response plot explorer here is looking at the data. Now, see, we've got a lot of constituent. If you can see these little gray lines in here, and that's sort of the constituent models. And so we're plotting the envelope of this, so the zone of uncertainty. The reality is that we haven't covered. I mean, this is a real-world plant. It's not covering the entire data space. It's got, you have operating conditions that are coupled, even though they're nominally independent. So if we were to increase the vapor flow but not increase anything else, we have a prediction, but we have an uncertainty around that prediction. And the same deal for both of them. If we come to the, if we sort by the observed values, and we go to the extreme, all right. So we have some uncertainty, but what we see is that our test set had been testing in the asking to extrapolate further. We get a lot more uncertainty at those data records. Now, just as a nicety here, if I want to deploy this model, I've got a couple different mechanisms, but I might want to hand it off to somebody else to look at it. I can export this Explorer and now I have a CDF that doesn't require either our data model or software, or Mathematica. I mean, it just strictly runs in the CDF player. So you can hand somebody a model, they can play the what ifs and see some of the responses. Okay, I'm going to run out of time, so I want to jump quickly to a slightly different project because this is something I think is sort of neat. So one of the issues that comes up, of course, is you got a lot of real-world data sets have binary, trinary, sort of low-order categoricals, true, false, survive, dead. In the case, so the Titanic survivals data, if we go pop into our data exploration, we see we have missing data. We also see our data summary table that we've got our, categorical inputs. So you either live or you die. But we're able to model with that now. Similarly, the display plots are going to automatically shift, so you're not connecting the dots between, because there is no middle ground between living and dying. Well, maybe some states. But so we've got that sort of mapping going on. If we go to analyzing the models, I can look at that, and we'll just pick a model to look at. I don't have an ensemble defined here. I've got, not very good models, but I've got, plots that automatically shift depending upon the nature of the output, so that I can see, because otherwise in this case we'd have a lineup of blue dots and a lineup, so we can see that we're actually getting some prediction, and I can shift that around even further and go to something like mushroom edibility, where it's either poisonous or not poisonous. And here I've got a purely categorical data set, and I'm able to do regression and model against that now, and sort of choose the threshold of how many, what's low enough order categorical. Is it 2 variables, 3 variables, 5 variables? If I have more than 5 and 95% of the data is in 5 variables, well, do I want to just sort of ignore the stuff that's outliers? That's can be done, and you still build models around the availability of information. Which factors, in this case of mushroom edibility, do you really care about in terms of betting your life that I'm hungry, I'm in the woods, Danny's in the woods someplace, and he's hungry, starving to death. Does he feel lucky? So on that note, I'm sort of out of time, so I'll open it up for questions, and I think what's really neat, though, is the ability to just sort of throw the data in, and even though it's missing data and now categorical, we can still get some insight out in terms of which variables are driving the behavior. I didn't talk about, we can look at data structures or their ratios, for example, that appear to be in successful models. Is that something that has meaning to us? Beta variables. So, okay, yes?
Navigating around this large user interface, and I'm wondering if there's correspondence between that and the underlying functions to make these decisions.
Yes. The large user interface is, this is 100% pure Mathematica. The GUI is just a massive dynamic module. But each of the named functions, like univariate plot, is in the function library. So there's correspondence that way.
So I'm not talking about how you were plotting, but you're making analysis decisions as you go through this. And is there a way to surface those analysis decisions in a code format?
Well, there is, not so much. I mean, everything, you can go retrieve the data and you can see what the functions look like. I can capture like this univariate plot and go to a report, and I can say move to report, select it, and then move to the report. And open the report, and what happens is, my round comments okay. Yes. All right, we got a little bug. Oh, I have to enable dynamics. Okay, so what I can do is as I go through, this just slides the stuff into a standard Mathematica notebook so that you can leave an audit trail. Because one of the neat things about a Mathematica notebook interface is you've got this sort of long audit trail of my analysis, and I can go back and repeat things. However, when you're talking about sort of this data analysis things, so now I've isolated down to which variables, now I want to pop back and go drill into just those variables. What's their scatter plot look like? What's their correlations look like? So you sort of have this interactive nature, which is really hard given the linear nature of a notebook interface. So the concept of having a documentation notebook that you can slide stuff in tries to leave the audit trail and the breadcrumbs. All of the models are saved to disk, within the folder structure. So, yes, Danny?
Yeah, a few slides back you mentioned this exporting to CDF, but I was wondering is what you export a model, does it also automatically export the underlying data?
Yes, it embeds the data within the model, because one of the problems of a CDF is that it can't go external, right? So this is so anybody that doesn't have enterprise Mathematica is still able to put something meaningful out there. So, and of course, it has to now it has to be 100% native Mathematica code for that. Okay. Yep.
How long did it take you to build this?
The interface, we would give credit to Ariel Sepulveda, who is, he's got a home in Puerto Rico, but it doesn't have any power or electricity or water at the moment. But I don't know, that means 3 years? 3 years, same, huh? Yeah, it was really, it was a sort of very much an iterative process. You start to things, you've got Ariel comes from a Windows environment, so it has no sense of color. So so Teresa and Katya were, explicitly choosing the colors to go across the tops for the different elements of the workflow. So what we tried to do is sort of, here are the tools, and then we tried to, in the GUI, get it mapped into the workflow that's appropriate. So that's, it's want to make it easy to do the right thing and hard to do the wrong thing. So, okay, any other questions? All right, thank you. It's a whirlwind tour, but tried to pack a lot in.